Question 1. Benchmark analysis indicates that a network administrator is tasked with configuring BGP to ensure that all traffic destined for a specific external service provider is consistently routed through a particular preferred Internet Service Provider (ISP) to optimize performance and meet Service Level Agreement (SLA) requirements. Considering the fundamental BGP path selection attributes and their typical use cases within a service provider network, which BGP attribute should be primarily manipulated to influence the as outbound traffic to prefer a specific ISP. Option A, as path prepend. Option B, local preference. Option C, MED multi-exit discriminator. Option D, default BGP path selection process. The correct answer is B, local preference. Explanation: scenario analysis. This scenario presents a professional challenge in network design and implementation, where a network administrator must select the most appropriate BGP path selection attribute for a specific service requirement. The challenge lies in understanding the nuanced impact of different BGP attributes on traffic flow, and ensuring that the chosen attribute aligns with the service's quality of service, (QoS), and performance expectations, while also adhering to Nokia's recommended practices for BGP services as outlined in the 4A0-114 exam syllabus. Misinterpreting the function or priority of these attributes can lead to suboptimal routing, increased latency, packet loss, or service degradation, directly impacting customer experience and potentially violating service level agreements, SLAs. Correct approach analysis. Selecting local preference as the primary BGP path selection attribute for influencing outbound traffic to a preferred ISP is the best professional practice in this context. Local preference is a well-understood BGP attribute that influences the exit point for traffic originating from the AS. By setting a higher local preference on routes learned from the preferred ISP, the AS will naturally prefer to send its outbound traffic through that ISP. This directly addresses the requirement of steering traffic towards a specific provider for service optimization, aligning with the principles of efficient BGP policy implementation for services. The 4A0-114 syllabus emphasizes understanding and manipulating BGP attributes for service delivery, and local preference is a key tool for this purpose. Incorrect approach is analysis. Choosing MED multi-exit discriminator as the primary attribute to influence outbound traffic is a regulatory and ethical failure. MED is primarily used to influence inbound traffic from neighboring ASes, signaling to them which path to use to reach the local AS. It is not designed to control the AS's own outbound traffic decisions. Relying on MED for outbound traffic steering would lead to unpredictable and incorrect routing, failing to meet the service requirement, and potentially violating the implicit ethical obligation to implement routing policies correctly and effectively. Using as path prepend to influence outbound traffic is also a significant failure, as path prepend is used to make a path appear longer to external ASes, thereby discouraging inbound traffic from using that path. While it influences path selection, its primary purpose is for inbound traffic control, not outbound. Using it for outbound traffic would be an incorrect application of the attribute, leading to suboptimal routing and failing to achieve the desired service outcome. This demonstrates a lack of understanding of fundamental BGP path selection mechanisms, which is a professional failing. Ignoring all BGP attributes and relying solely on the default BGP path selection process is a failure to implement effective network policy. The default BGP path selection process, while functional, does not allow for granular control over traffic flow based on specific service requirements. For a service that needs to be directed to a preferred ISP, active policy configuration is necessary. Failing to configure such policies means the network is not being optimized for the service, which is a professional oversight and a failure to meet the implicit requirement of providing a well-managed and performant service. Professional reasoning. Professionals should approach such scenarios by first clearly defining the service requirement, specifically how traffic should flow. Then, they must consult their knowledge of BGP attributes, understanding their intended purpose and impact on path selection for both inbound and outbound traffic. The 4A0-114 syllabus provides the foundational knowledge for this. The decision-making process involves mapping the service requirement to the most appropriate BGP attribute that can influence the desired traffic flow. In this case, outbound traffic steering directly points to local preference. if the requirement were for inbound traffic. Other attributes like MED or as path prepend might be considered, but their application would be different. Always prioritize attributes designed for the specific traffic flow direction and purpose. When in doubt, refer to vendor documentation, Nokia in this case, and established BGP best practices. Question 2. Cost-benefit analysis shows that implementing a more sophisticated BGP path selection strategy for equal-cost multipath scenarios can reduce operational overhead and improve service delivery metrics, but requires careful configuration. Considering the Nokia Border Gateway Protocol Fundamentals for Services exam syllabus, which of the following approaches best aligns with optimizing BGP path selection for services when multiple equal-cost paths are available? Option A. Configuring BGP local preference on outbound advertisements to favor specific paths, thereby influencing inbound traffic selection by neighboring ASEs. Option B. Manually adjusting the BGP MED multi-exit discriminator attribute on inbound advertisements to influence path selection by neighboring ASEs. Option C. Relying solely on the default BGP path selection algorithm without any explicit configuration, assuming it will automatically choose the most optimal path for all services. Option D. Implementing a random selection mechanism for equal-cost paths to distribute traffic unpredictably across available links. The correct answer is A. Configuring BGP local preference on outbound advertisements to favor specific paths, thereby influencing inbound traffic selection by neighboring ASEs. Explanation. The scenario presents a common challenge in network engineering, balancing the immediate need for network stability and performance with the long-term implications of configuration choices. Specifically, the decision of how to handle BGP path selection when multiple equal-cost paths exist and the potential for suboptimal traffic flow requires careful consideration of BGP attributes and their impact on service delivery. The professional challenge lies in understanding the nuances of BGP's decision-making process and how to influence it to achieve desired outcomes without introducing instability or violating service-level agreements, SLAs. The correct approach involves a deep understanding of BGP's path selection algorithm and the strategic manipulation of attributes like local preference to influence which path is preferred. This aligns with best professional practice by ensuring that traffic is routed efficiently, minimizing latency and maximizing bandwidth utilization, thereby meeting or exceeding customer SLAs. It demonstrates a proactive approach to network optimization, preventing potential service degradation and associated penalties. From a regulatory and ethical standpoint, this approach upholds the responsibility to provide reliable and performant services as promised to customers. An incorrect approach would be to rely solely on the default BGP path selection process without any explicit configuration for equal-cost paths. This could lead to unpredictable traffic patterns, potentially sending traffic over longer or more congested links, negatively impacting service quality. This failure to actively manage path selection could be seen as a breach of professional duty to optimize network performance and could lead to regulatory scrutiny if SLAs are consistently missed. Another incorrect approach would be to arbitrarily assign weights or preferences without a clear understanding of their impact, potentially destabilizing the network or creating new suboptimal routing scenarios. This demonstrates a lack of technical rigor and could be considered negligent. The professional reasoning process should involve 1. Identifying the problem, recognizing that multiple equal-cost paths exist and that the default selection might not be optimal. 2. Understanding the tools, recalling the BGP path selection algorithm and the available attributes for influencing it. 3. Analyzing the impact, considering the business and technical implications of each potential path selection outcome. 4. Implementing and verifying, configuring the chosen attribute e.g., local preference, and thoroughly verifying the resulting path selection and traffic flow. 5. Documenting, recording the decision-making process and the configuration changes for future reference and auditing. Question 3. Which approach would be most effective and professionally sound for influencing inbound traffic to a specific service hosted within an autonomous system, ensuring that traffic preferentially enters the AS through a designated edge router, while adhering to standard BGP operational principles? Option A. Modifying the as path attribute of BGP routes advertised to external peers to make certain ingress points appear shorter. Option B, implementing a static routing policy on all edge routers to force traffic toward the service's location. Option C, adjusting the MED attribute on BGP routes received from external peers to signal a preference for specific ingress points. Option D, manipulating the local pref attribute on inbound BGP advertisements to influence the preference of internal BGP peers. The correct answer is D, manipulating the local pref attribute on inbound BGP advertisements to influence the preference of internal BGP peers. Explanation: this scenario presents a professional challenge in network design and implementation, where the efficient and reliable exchange of routing information is paramount. The challenge lies in selecting the most appropriate BGP attribute manipulation strategy to influence path selection without compromising network stability or violating established routing policies. Careful judgment is required to balance performance goals with the need for predictable and secure routing behavior. The correct approach represents best professional practice because it leverages BGP's inherent flexibility in a controlled and predictable manner. By manipulating the local pref attribute, network administrators can influence inbound traffic flow at the edge of their autonomous system, in a way that is understood and respected by internal BGP peers. This method is widely accepted and documented within BGP best practices, aligning with the goal of optimizing traffic engineering without introducing unnecessary complexity or potential for routing loops. It directly addresses the need to prefer a specific ingress point for traffic destined to the AS, a common requirement for services hosted within that AS. An incorrect approach that involves manipulating as path length to influence inbound traffic would be professionally unacceptable. This is because as path is primarily an indicator of the path to reach a destination, and manipulating it to influence inbound traffic is a violation of standard BGP routing principles. Such manipulation can lead to suboptimal routing for other ASes, potentially causing congestion or increased latency for traffic not originating from or destined to the specific service. It can also be perceived as an attempt to hijack traffic or unfairly influence routing decisions, which can damage inter-AS relationships and lead to BGP route flapping or policy enforcement by other network operators. Furthermore, relying on as path for inbound traffic control can create unpredictable routing behavior and make troubleshooting significantly more difficult. Another incorrect approach would be to solely rely on MED, multi-exit discriminator, for influencing inbound traffic. While MED is designed to influence traffic entering and AS from a neighboring AS, its effectiveness is limited to direct peering relationships and can be overridden by other BGP attributes or policies. It is not a reliable or comprehensive method for controlling inbound traffic across multiple peering points or for influencing traffic destined for specific services within the AS. Using MED in isolation for this purpose would lead to inconsistent and unreliable path selection. The professional decision-making process for similar situations should involve a thorough understanding of BGP attributes and their intended use. Network engineers must first define the desired traffic flow behavior, considering factors like service location, peering points, and potential congestion. They should then evaluate which BGP attributes can achieve this behavior in a stable and predictable manner, prioritizing attributes that are designed for local policy enforcement, like local pref, over those intended for inter-AS path discovery, like as path. Consulting BGP best practices and vendor documentation is crucial. Finally, any proposed changes should be tested in a lab environment or during a scheduled maintenance window to verify their impact before full deployment. Question 4. The review process indicates a need to ensure network engineers can correctly identify the primary BGP path selection attribute used by a Nokia router to influence outbound traffic to a specific external network, given a scenario where multiple BGP paths exist with varying configurations. Which BGP attribute is most commonly manipulated by service providers to influence their own outbound traffic flow to a particular destination network? Option A, MED. Option B, origin. Option C, as path. Option D, wait. The correct answer is D, wait. Explanation: the review process indicates a need to assess the understanding of BGP path selection attributes in a service provider context, specifically focusing on how these attributes influence traffic engineering decisions. This scenario is professionally challenging because misinterpreting or misapplying BGP attributes can lead to suboptimal routing, increased latency, inefficient bandwidth utilization, and potential service disruptions. Network engineers must possess a nuanced understanding of these attributes to ensure network stability, performance, and adherence to service-level agreements, SLAs. The Nokia 4A0-114 exam specifically tests this foundational knowledge for service provider environments. The correct approach represents best professional practice because it prioritizes the most influential BGP path selection attributes in a logical, hierarchical order as defined by BGP itself and commonly implemented in service provider networks. This systematic evaluation ensures that the most desirable path, according to network policy and operational requirements, is consistently chosen. Adherence to this established order prevents unpredictable routing behavior and aligns with the principles of robust network design and management. An incorrect approach that prioritizes local preference over weight, for instance, would be a regulatory failure in the context of BGP's defined path selection algorithm. Local preference is a well-defined BGP attribute used for influencing outbound traffic, but it is evaluated asterisk after asterisk weight. Ignoring this hierarchy leads to incorrect path selection. Similarly, an approach that incorrectly assumes as path length is the primary determinant for outbound traffic engineering would be a significant operational failure, as path is crucial for inbound traffic selection and preventing routing loops, but it is evaluated asterisk after asterisk local preference and MED. Prioritizing an attribute that is not the most influential for the specific traffic engineering goal, outbound traffic, demonstrates a lack of fundamental understanding and can lead to routing policies that are ineffective or counterproductive. An approach that overlooks the importance of BGP communities for policy enforcement would also be a failure. While not a direct path selection attribute in the same vein as weight or local preference, communities are critical for signaling and influencing path selection decisions at peer routers, and their misapplication or omission can lead to unintended routing consequences. Professionals should employ a decision-making framework that begins with understanding the objective e.g., influencing outbound traffic to a specific destination. They should then systematically consider BGP path selection attributes in their defined order of preference. Weight, then local preference, then as path, then origin, then MED, then eBGP over iBGP, then lowest IGP cost to next hop, then oldest route, then router ID, then neighbor IP address. For traffic engineering, weight and local preference are typically the most manipulated attributes for outbound traffic. Understanding how each attribute influences the decision-making process and in what order is paramount. Question 5. The analysis reveals that a critical customer prefix is experiencing intermittent reachability due to rapid BGP route advertisements and withdrawals. The network operations team needs to restore stable connectivity for this prefix as quickly as possible, while minimizing any potential negative impact on other services. Which of the following actions represents the most professional and effective initial response to diagnose and resolve this BGP route flap? Option A. Examine the BGP neighbor state, review BGP logs for error messages related to the session, and analyze the attributes of the received and advertised routes for the affected prefix. Option B. Initiate a hardware diagnostic on the local router's network interface card, NIC, that handles the BGP session, suspecting a physical layer issue. Option C. Immediately disable the BGP peering session with the neighbor advertising the flapping prefix to prevent further instability. Option D. Remove the local BGP policy configuration applied to the affected prefix, assuming it is causing the instability. The correct answer is C. Immediately disable the BGP peering session with the neighbor advertising the flapping prefix to prevent further instability. Explanation. The analysis reveals a common challenge in network operations where a BGP route flap, characterized by rapid changes in reachability for a specific prefix, impacts service availability. This scenario is professionally challenging because it directly affects customer services, potentially leading to revenue loss, reputational damage, and increased support overhead. The urgency to resolve such issues requires a systematic and informed approach, balancing immediate action with long-term stability. The correct approach involves a methodical investigation of the BGP session and the affected prefix. This includes examining BGP neighbor states, looking for specific error messages or flapping indicators, and analyzing the attributes of the received and advertised routes for the problematic prefix. The goal is to identify the root cause, whether it's a configuration error, a transient network issue, or a policy misconfiguration. This aligns with best professional practices by prioritizing service restoration while ensuring network stability and adherence to operational guidelines. In the context of Nokia BGP fundamentals for services, this methodical approach is crucial for maintaining the integrity and performance of the border gateway protocol, which underpins interdomain routing and service delivery. An incorrect approach would be to immediately disable the BGP peering session without proper diagnosis. This is professionally unacceptable because it is an overly aggressive action that can disrupt connectivity for a much wider set of prefixes and customers than the initially affected one. It bypasses the diagnostic steps necessary to pinpoint the actual problem, potentially masking underlying issues that could recur. This action fails to uphold the principle of least disruption and can lead to unintended consequences, violating operational best practices. Another incorrect approach is to solely focus on the local router's configuration for the affected prefix, ignoring the BGP neighbor's state and advertised routes. This is a failure to consider the distributed nature of BGP. The problem might originate from the neighbor or be a result of the interaction between the two routers. Neglecting to examine the BGP session status and the routes exchanged with the neighbor means missing critical information that could quickly identify the source of the flap. This demonstrates a lack of comprehensive troubleshooting, which is a regulatory and ethical failure in maintaining reliable network services. A third incorrect approach is to assume the issue is a hardware failure and initiate a hardware replacement without exhausting software and configuration troubleshooting steps. While hardware can fail, BGP route flaps are far more commonly caused by software, configuration, or transient network conditions. This approach is inefficient, costly, and delays the resolution of the actual problem. It represents a failure to follow a logical troubleshooting methodology and can lead to unnecessary downtime and resource expenditure, contravening professional responsibility. The professional decision-making process for similar situations should involve a structured troubleshooting framework. This typically includes 1. Problem identification. Clearly define the scope and impact of the issue. 2. Information gathering. Collect relevant logs, BGP state information and traffic statistics. 3. Hypothesis generation. Formulate potential causes based on the gathered information. 4. Testing and validation. Systematically test each hypothesis starting with the most probable. 5. Resolution. Implement the solution and verify its effectiveness. 6. Documentation. Record the problem, the steps taken, and the resolution for future reference and knowledge sharing. This systematic approach ensures that solutions are effective, efficient, and minimize disruption. Question 6. System analysis indicates that a Nokia router is unexpectedly advertising a specific internal prefix to an external peer, which is causing routing instability for downstream customers. The network operations team needs to quickly identify and rectify the BGP configuration responsible for this incorrect advertisement. Which of the following diagnostic approaches is the most effective and professionally sound for isolating the misconfiguration? Option A. Immediately initiate a full BGP table reset for all neighbors to clear any potential state corruption. Option B. Examine the BGP neighbor status and the advertised routes for the specific external peer, correlating this with any recent configuration changes applied to the BGP process or relevant route maps and prefix lists. Option C. Begin making random adjustments to the route map policies applied to various internal BGP neighbors until the advertisement stops. Option D. Focus solely on the ingress filters applied to the external peer, assuming the issue must be related to what is being received. The correct answer is B. Examine the BGP neighbor status and the advertised routes for the specific external peer, correlating this with any recent configuration changes applied to the BGP process or relevant route maps and prefix lists. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a misconfiguration in BGP, specifically related to route advertisement, can have widespread impact. The professional challenge lies in quickly identifying the root cause of unexpected route propagation without disrupting existing services or causing further network instability. The urgency stems from the potential for service degradation or outage for customers relying on the affected routes. Careful judgment is required to balance the need for rapid resolution with the risk of introducing new problems through hasty changes. Correct approach analysis. The correct approach involves a systematic and evidence-based investigation. This means leveraging BGP's inherent diagnostic tools and operational best practices. Specifically, examining BGP neighbor states, received and advertised routes, and the impact of any recent configuration changes is paramount. The Nokia BGP implementation provides commands to inspect these aspects, allowing for precise identification of where the misconfiguration occurred, e.g., an incorrect prefix list, route map, or neighbor-specific policy. This methodical approach aligns with industry best practices for network troubleshooting, minimizing the risk of unintended consequences and ensuring a swift, accurate resolution. It also implicitly adheres to service-level agreements, SLAs, by aiming for minimal downtime. Incorrect approaches analysis. One incorrect approach is to immediately revert all recent configuration changes without proper analysis. This is a shotgun approach that, while sometimes effective, can be disruptive and may not address the actual root cause if the issue is more complex than a single recent change. It fails to demonstrate a professional understanding of BGP's behavior and can lead to further instability if the reverted change was actually necessary for other services. Another incorrect approach is to focus solely on the symptoms observed at the edge of the network, without tracing the BGP path and policies. This ignores the distributed nature of BGP and the possibility that the issue originates from an upstream or internal peer. It represents a failure to apply a structured troubleshooting methodology and can lead to wasted effort and prolonged outages. A third incorrect approach is to make speculative configuration changes on multiple BGP neighbors simultaneously in an attempt to fix the problem. This is highly risky, as it increases the probability of introducing new, unforeseen issues and makes it difficult to isolate the impact of any single change. It demonstrates a lack of discipline and a disregard for the potential cascading effects of BGP misconfigurations. Professional reasoning. Professionals should approach such situations by first gathering information about the observed symptoms and the scope of the impact. Then, they should systematically examine the BGP configuration and operational state, starting from the affected peers and working inwards or outwards as dictated by the evidence. This involves using diagnostic commands to verify neighbor states, route tables, and policy application. If recent changes are suspected, they should be reviewed in conjunction with the current BGP state. The decision to revert or modify configurations should be based on clear evidence and a thorough understanding of the potential impact. Documenting all steps taken and their observed effects is crucial for post-incident analysis and future learning. Question 7. The control framework reveals that a critical BGP peering session with a service provider is intermittently flapping. The network operations team needs to restore stable connectivity as quickly and safely as possible. Which of the following diagnostic and resolution approaches best aligns with operational best practices for BGP stability? Option A. Systematically verify the local BGP configuration, interface status, and router logs for any anomalies related to the specific neighbor before considering external factors. Option B. Begin a deep dive into the service provider's network topology and routing policies to identify potential external causes. Option C. Immediately reset the BGP session on the local router and inform the service provider of a potential remote issue. Option D. Apply a blanket policy change to all BGP sessions to increase timers, assuming a general network congestion issue. The correct answer is C. Immediately reset the BGP session on the local router and inform the service provider of a potential remote issue. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a critical BGP peering session experiences intermittent instability. The professional challenge lies in diagnosing the root cause without disrupting service further, especially in a production environment. The need for a systematic approach is paramount, balancing the urgency of restoration with the risk of exacerbating the problem. The complexity arises from the distributed nature of BGP and the potential for issues to stem from either the local router, the remote peer, or the intervening network path. Correct approach analysis. The correct approach involves a methodical investigation starting with the most immediate and controllable factors. This includes verifying the local BGP configuration for the specific neighbor, checking interface status, and examining local logs for error messages related to the peering session. This aligns with best practices for network troubleshooting, which prioritize isolating the problem to the smallest possible scope. By focusing on the local router first, the engineer can quickly rule out or confirm internal misconfigurations or hardware issues. This systematic approach minimizes the risk of unintended consequences and ensures that any changes made are targeted and documented. In the context of BGP, this methodical verification is crucial for maintaining routing stability and adhering to operational guidelines that emphasize proactive monitoring and controlled troubleshooting. Incorrect approaches analysis. Immediately attempting to reset the BGP session without prior investigation is a failure to adhere to controlled change management procedures. This approach risks causing a more prolonged outage if the underlying issue is not a simple session flap, but a more complex configuration or network problem. Bypasses the essential diagnostic steps required to understand the root cause, potentially leading to repeated failures and increased downtime. Focusing solely on the remote peer's configuration or network without first verifying the local environment is an inefficient use of resources and time. While the remote peer could be the cause, assuming this without local verification is premature and can lead to unnecessary escalations or communication overhead. It fails to follow a logical troubleshooting methodology that starts with what is directly observable and controllable. Implementing broad, sweeping configuration changes across multiple BGP neighbors or the entire routing instance without a specific diagnosis is a significant operational risk. This approach is akin to shotgun troubleshooting and can introduce new, unforeseen problems, potentially impacting a much larger portion of the network than the original issue. It violates principles of least privilege and targeted problem solving, increasing the likelihood of unintended service degradation. Professional reasoning. Professionals should adopt a structured troubleshooting methodology. This typically involves 1. Understanding the problem, clearly define the symptoms and impact. 2. Gathering information, collect logs, interface statistics, and configuration details. 3. Formulating hypotheses, develop potential causes based on the gathered information. 4. Testing hypotheses, systematically verify each hypothesis starting with the most likely or easiest to test. 5. Implementing solutions, apply changes in a controlled manner with rollback plans. 6. Verifying resolution, confirm the problem is fixed and monitor for recurrence. This process ensures that troubleshooting is efficient, effective, and minimizes risk to the production network. Question 8. During the evaluation of a network outage where a specific customer prefix is intermittently unreachable, network engineers observe that traffic is not flowing through the expected optimal path. The BGP configuration appears syntactically correct, but the routing table on several edge routers shows a less preferred path being selected for this prefix. What is the most effective approach to diagnose and resolve this issue? Option A. Remove and re-add the BGP neighbor configurations for the affected customer prefix to force a full BGP session re-establishment. Option B. Implement a network-wide BGP route dampening policy to stabilize routing, as the intermittent nature suggests instability. Option C. Immediately restart the BGP processes on all edge routers involved in the path to the customer prefix, assuming a transient BGP state issue. Option D. Analyze the BGP attributes associated with the prefix on the affected routers, specifically focusing on as path, local pref, and med, to understand the path selection process and identify any discrepancies or unexpected values. The correct answer is D. Analyze the BGP attributes associated with the prefix on the affected routers, specifically focusing on as path, local pref, and med, to understand the path selection process and identify any discrepancies or unexpected values. Explanation. This scenario presents a common challenge in network operations where a critical routing protocol, BGP, is exhibiting unexpected behavior impacting service availability. The professional challenge lies in quickly and accurately diagnosing the root cause while minimizing service disruption. The need for a systematic and evidence-based approach is paramount, especially when dealing with a protocol as foundational to Internet routing as BGP. Adhering to established operational procedures and understanding the nuances of BGP attributes is crucial for effective troubleshooting. The correct approach involves a methodical examination of BGP attributes and path selection, directly correlating observed behavior with the BGP decision process. This aligns with best professional practices by focusing on verifiable data and the established mechanisms of the protocol. By analyzing the specific attributes influencing path selection, such as path, local pref, and med, the engineer can pinpoint the misconfiguration or unexpected interaction causing the suboptimal routing. This systematic analysis ensures that the resolution is targeted and effective, preventing recurrence and maintaining service integrity. An incorrect approach that focuses solely on restarting BGP processes without understanding the underlying cause is professionally unacceptable. This is akin to treating a symptom without diagnosing the disease. It risks temporary resolution while leaving the root cause unaddressed, potentially leading to repeated issues. Furthermore, it bypasses the critical step of analyzing BGP attributes, which is essential for understanding why a particular path was chosen or rejected. This lack of analytical rigor can lead to misinterpretations and incorrect fixes, potentially exacerbating the problem or introducing new ones. Another incorrect approach that involves making broad configuration changes across the network without specific evidence is also professionally unsound. This shotgun approach is inefficient and carries a high risk of unintended consequences, potentially disrupting other services or creating new routing loops. It demonstrates a failure to apply a structured troubleshooting methodology, which is a cornerstone of professional network engineering. Such actions can lead to significant service degradation and are difficult to roll back cleanly. The professional decision-making process in such a situation should involve 1. Clearly defining the observed problem and its impact. 2. Gathering relevant data, BGP neighbor states, routing tables, BGP attribute dumps. 3. Forming hypotheses based on the data and knowledge of BGP behavior. 4. Testing hypotheses systematically by examining specific BGP attributes and path selection. 5. Implementing the most likely solution based on evidence. And 6. Verifying the resolution and monitoring for recurrence. This structured approach ensures that actions are data-driven, efficient, and minimize risk. Question 9. Market research demonstrates a growing demand for a new premium service that requires predictable low latency and specific inbound traffic routing from the customer's network. The service provider's network architecture utilizes BGP for routing. To meet the customer's service level agreement, SLA, for this new service, the network engineering team needs to influence how traffic from the customer's edge router is directed towards the provider's core network for this specific service. The goal is to ensure that the provider's internal routers prefer a particular path for this service's traffic, originating from the customer, which BGP attribute manipulation strategy is the most appropriate and professionally sound approach to achieve this traffic engineering objective within the provider's autonomous system. Option A. Manipulate the as-path attribute to make the preferred path appear shorter to internal routers. Option B. Advertise the routes for the new service with a lower origin attribute, e.g., IG, compared to other routes. Option C. Configure a higher local preference value on the routes learned from the customer's edge router that are destined for the new service. Option D. Adjust the MED multi-exit discriminator on the routes advertised to the customer's edge router. Correct answer is A. Manipulate the as-path attribute to make the preferred path appear shorter to internal routers. Explanation. Scenario analysis. This scenario presents a professional challenge related to network design and BGP route propagation within a service provider context. The core difficulty lies in balancing the need for efficient and stable routing with the potential for unintended consequences arising from policy misconfigurations. Specifically, the introduction of a new customer service that requires specific traffic engineering considerations, such as influencing path selection, necessitates a deep understanding of BGP attributes and their manipulation. A misstep in configuring these policies can lead to suboptimal routing, increased latency, service degradation, and potentially network instability, impacting multiple customers. The pressure to deploy new services quickly, while ensuring network integrity, demands meticulous planning and validation. Correct approach analysis. The correct approach involves leveraging BGP's path attributes, specifically local preference, to influence inbound traffic flow for the new service. Local preference is a well-understood BGP attribute that is only considered within an autonomous system, as by setting a higher local preference on routes learned from the customer's edge router that are destined for the new service, the provider's internal routers will prefer these paths. This is the standard and most effective method for influencing inbound traffic within as without impacting external routing policies or requiring complex as-path manipulation. This approach aligns with best practices for traffic engineering, ensuring that traffic destined for the new service takes the most optimal path as defined by the provider's internal policies, thereby meeting the customer's requirements for predictable performance and low latency. It is a direct and controlled method of influencing traffic flow, minimizing the risk of unintended side effects. Incorrect approaches analysis. One incorrect approach would be to manipulate the as-path attribute to influence inbound traffic. The as-path attribute is primarily used by external BGP peers to determine the best path based on the number of as-hops, modifying the as-path for inbound traffic within the providers, as is not its intended purpose, and can lead to unpredictable routing behavior for other ASs, potentially causing routing loops or black holes. This violates the fundamental principles of BGP path selection and can have widespread negative impacts on inter-AS routing stability. Another incorrect approach would be to rely solely on MED, multi-exit discriminator. MED is an attribute used to influence inbound traffic from an external, but its effectiveness is limited and depends on the configuration of the neighboring AS. It is not a reliable mechanism for controlling inbound traffic within the provider's own AS, especially when specific path preference is required for a new service. Furthermore, relying on MED for internal traffic engineering is a misapplication of the attribute and would likely fail to achieve the desired outcome. A further incorrect approach would be to advertise routes with a lower origin attribute e.g. IGP over EGP to influence inbound traffic. The origin attribute is a primary factor in BGP path selection, but it is used to determine the best path when multiple routes to the same prefix exist from different sources. Manipulating the origin attribute for the purpose of influencing inbound traffic for a specific service within the providers, as is a misinterpretation of its function, and would likely lead to incorrect routing decisions for all prefixes, not just the new service. It does not provide the granular control needed for this specific traffic engineering requirement. Professional reasoning. When faced with a requirement to influence inbound traffic for a specific service, professionals should first consult the network design documentation and understand the capabilities of BGP path attributes. The decision-making process should prioritize using attributes designed for internal as traffic engineering, such as local preference. A thorough understanding of how each BGP attribute functions and its scope of influence within SVS between ASs is crucial. Before implementing any changes, a detailed impact analysis should be performed, considering potential effects on other services and network stability. Configuration changes should be tested in a lab environment or during a scheduled maintenance window with rollback plans in place. Continuous monitoring after deployment is essential to verify that the desired traffic flow is achieved and that no adverse effects are observed. Question 10. Risk assessment procedures indicate that a critical customer service is experiencing intermittent connectivity issues, and preliminary network monitoring suggests that Border Gateway Protocol (BGP) sessions with key transit providers are flapping or not fully establishing. Network engineers suspect that the routing information being exchanged might be incorrect, leading to traffic being misdirected. What is the most appropriate initial course of action to diagnose and resolve this BGP-related service degradation? Option A. Focus exclusively on verifying the physical layer connectivity and interface status for all BGP peering links, as link instability is the most probable cause of BGP session issues. Option B. Immediately initiate a BGP reset on all affected peering sessions with transit providers to force re-establishment and observe if the issue resolves. Option C. Conduct a thorough review of the BGP neighbor states, examine the received and advertised prefixes, and analyze key BGP attributes, e.g., as path, local preference, for anomalies or policy violations that could explain the routing instability and service impact. Option D. Implement a broad change to BGP import and export policies across all transit provider peerings, assuming a global policy misconfiguration is the most likely cause. The correct answer is B. Immediately initiate a BGP reset on all affected peering sessions with transit providers to force reestablishment and observe if the issue resolves. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a critical routing protocol, BGP, is exhibiting unexpected behavior that impacts service availability. The challenge lies in quickly and accurately diagnosing the root cause without further disrupting services or violating operational best practices. The pressure to restore service rapidly can lead to hasty decisions, making a systematic and informed approach crucial. The complexity of BGP, with its numerous attributes and configuration options, further complicates troubleshooting. Correct approach analysis. The correct approach involves a methodical examination of BGP neighbor states and the received routing information. This aligns with best professional practices for network troubleshooting, emphasizing data-driven analysis. Specifically, verifying the BGP session status, e.g., established, and inspecting the received prefixes and their attributes, like as path, med, local preference, is fundamental to understanding how routes are being learned and propagated. This systematic approach allows for the identification of misconfigurations, policy violation, or unexpected route advertisements that could be causing the service degradation. This is directly supported by the principles of network operational integrity and service assurance, which are paramount in maintaining customer trust and meeting service-level agreements. Incorrect approaches analysis. One incorrect approach is to immediately reset BGP sessions without a clear understanding of the cause. This is a brute force method that can temporarily resolve an issue, but fails to address the underlying problem, potentially leading to its recurrence. It also risks further service disruption if the reset itself causes unexpected state changes or if the problem is not session-related. This approach demonstrates a lack of analytical rigor and a failure to adhere to structured troubleshooting methodologies. Another incorrect approach is to unilaterally change BGP policies on all neighbors without specific evidence pointing to a policy issue. This is a broad, untargeted action that could have unintended consequences, potentially blocking legitimate routes or creating new routing loops. It bypasses the diagnostic phase and relies on guesswork, which is unprofessional and can lead to significant service degradation. This action violates the principle of least privilege and careful change management. A third incorrect approach is to focus solely on the physical layer connectivity of the BGP peers. While physical connectivity is a prerequisite for BGP, the described issue, service degradation due to incorrect routing, strongly suggests a problem at the BGP protocol level, not a physical link failure. Investigating the physical layer without first examining the BGP state and attributes is inefficient and diverts resources from the actual problem domain. This demonstrates a failure to correctly prioritize troubleshooting steps based on the presented symptoms. Professional reasoning. Professionals facing such a situation should employ a structured troubleshooting framework. This typically involves 1. Understanding the symptoms, clearly define the observed service degradation. 2. Gathering information, collect relevant logs, BGP neighbor states, and routing tables. 3. Formulating hypotheses. Based on the symptoms and gathered information, propose potential causes. 4. Testing hypotheses. Systematically test each hypothesis using diagnostic commands and by examining protocol behavior. 5. Implementing solutions. Once the root cause is identified, implement the most targeted and least disruptive solution. 6. Verifying the fix. Confirm that the service has been restored and the issue is resolved. 7. Documenting the incident. Record the problem, its cause, and the resolution for future reference and knowledge sharing. This systematic process ensures that actions are data-driven, minimizes the risk of further disruption, and leads to a sustainable resolution. Question 11. Regulatory review indicates that a network operator is experiencing intermittent BGP routing anomalies. The engineering team is considering several approaches to address these issues, focusing on the validation of BGP attributes exchanged with external peers, which approach best aligns with the regulatory expectation of providing secure and reliable network services. Option A. Implement strict validation of as path to prevent loops and ensure legitimate route propagation, and enforce validation of the next HOP attribute to ensure traffic is directed to reachable and authorized destinations. Option B. Disable as path validation and accept any next HOP value to reduce the complexity of BGP configuration and troubleshooting. Option C. Rely solely on the trust established with external BGP peers and forego any internal validation of BGP attributes. Option D. Deactivate all BGP attribute validation mechanisms to simplify the overall BGP configuration and minimize potential operational errors. The correct answer is A. Implement strict validation of as path to prevent loops and ensure legitimate route propagation, and enforce validation of the next HOP attribute to ensure traffic is directed to reachable and authorized destinations. Explanation. Scenario analysis. This scenario presents a professional challenge related to the implementation of BGP security features, specifically the validation of BGP attributes. Network engineers are tasked with ensuring that BGP routing information exchanged between autonomous systems is not only functional, but also secure and trustworthy. The challenge lies in balancing the need for robust security validation with the operational realities of a dynamic network environment, where misconfigurations or transient issues can occur. Failure to properly validate BGP attributes can lead to suboptimal routing, network instability, or even security breaches where malicious actors could inject false routing information. The regulatory framework for telecommunications, while not always explicitly detailing BGP attribute validation, mandates the provision of reliable and secure network services. Therefore, adherence to best practices in BGP security is implicitly required to meet these broader regulatory obligations. Correct approach analysis. The correct approach involves implementing a comprehensive validation strategy for BGP attributes, focusing on critical attributes like as path and next HOP. This aligns with the principles of network security and operational integrity, which are foundational to meeting regulatory requirements for service reliability. By actively checking the integrity and expected values of these attributes, network operators can detect and mitigate potential routing anomalies or malicious injections. This proactive stance is essential for maintaining a stable and predictable network, thereby fulfilling the implicit regulatory duty to provide dependable services. This approach demonstrates due diligence in network management and security. Incorrect approaches analysis. Ignoring as path validation and accepting any next HOP value represents a significant regulatory and ethical failure. The as-path attribute is crucial for preventing routing loops and ensuring that routes are advertised through legitimate sequences of autonomous systems. Failing to validate it opens the network to routing loops and denial of service attacks. Similarly, accepting any next HOP value without verification can lead to traffic being misdirected to unauthorized or non-existent destinations, compromising network integrity and service availability. This approach violates the implicit regulatory obligation to maintain a secure and reliable network. Relying solely on external BGP peer trust without internal validation is another failure. While trust between directly connected BGP peers is a starting point, it does not account for potential misconfigurations or compromises within those peers' networks that could propagate incorrect or malicious routing information. This lack of internal validation creates a blind spot, making the network vulnerable to transitive trust issues and failing to meet the standard of care expected for network security. Disabling all BGP attribute validation to simplify configuration is a direct contravention of best practices and implicitly violates regulatory expectations for network security and reliability. Simplification should never come at the expense of fundamental security controls. This approach prioritizes ease of management over the integrity of the routing system, exposing the network to a wide range of security threats and operational failures, thereby failing to meet regulatory mandates for service provision. Professional reasoning. Professionals should adopt a risk-based approach to BGP attribute validation. This involves understanding the criticality of each BGP attribute and the potential impact of its misconfiguration or malicious manipulation. The decision-making process should prioritize implementing robust validation mechanisms for attributes that directly impact routing stability and security, such as path and next hop. When faced with operational challenges, the focus should be on troubleshooting and resolving the underlying issues causing validation failures rather than disabling security features. This requires a deep understanding of BGP, network security principles, and the relevant regulatory expectations for service providers. Continuous monitoring and periodic review of validation policies are also essential to adapt to evolving threats and network changes. Question 12. The performance metrics show a significant increase in latency for a critical customer service delivered over BGP-peered networks. Initial observations suggest a potential issue with BGP path selection influencing the traffic flow. Which of the following diagnostic steps best aligns with best professional practice and regulatory expectations for ensuring service continuity and stability? Option A. Focus solely on the customer's edge router configuration, assuming the issue must originate from their equipment, and make broad configuration changes there. Option B. Analyze the BGP routing policies and attributes, e.g., local preference as path med, for the affected prefixes to understand how the best path is being selected and if it deviates from the optimal path for the service. Option C. Arbitrarily adjust BGP timers, e.g., keep a live hold time, across all BGP peers to expedite route updates and potentially improve convergence. Option D. Immediately reset all BGP sessions involved in the path to the customer to force a reconvergence and hope for a better path selection. The correct answer is B. Analyze the BGP routing policies and attributes, e.g., local preference as path med, for the affected prefixes to understand how the best path is being selected and if it deviates from the optimal path for the service. Explanation. The scenario presents a common challenge in network operations where performance degradation is observed, and the immediate inclination might be to implement a quick fix without fully understanding the underlying cause. This is professionally challenging because network engineers are under pressure to restore service rapidly, which can lead to hasty decisions that might have unintended consequences or fail to address the root problem. The Nokia Border Gateway Protocol Fundamentals for Services exam emphasizes understanding BGP's role in service delivery and the importance of adhering to operational best practices and regulatory compliance, even in high-pressure situations. The correct approach involves a systematic investigation of BGP routing policies and configurations. This aligns with best professional practice by ensuring that any changes made are informed, targeted, and have a minimal impact on other services. Specifically, examining BGP attributes like local preference, as path and med, and understanding how they influence path selection is crucial for diagnosing and resolving routing issues that affect service performance. This methodical approach ensures that the network remains stable and compliant with service-level agreements, SLAs, which are often implicitly or explicitly governed by regulatory frameworks that mandate reliable service delivery. Adhering to documented operational procedures and change management processes, which are often influenced by regulatory requirements for network stability and security, is paramount. An incorrect approach of immediately resetting BGP sessions without a thorough analysis is professionally unacceptable. This action bypasses the diagnostic process and can lead to unpredictable routing changes, potentially disrupting other services or creating security vulnerabilities. From a regulatory perspective, such an action could be seen as a failure to exercise due diligence in maintaining network stability and service availability, potentially violating service assurance mandates. Another incorrect approach, such as arbitrarily modifying BGP timers to influence convergence speed, is also problematic. While timers are configurable, altering them without understanding their impact on network stability and the specific service requirements can lead to flapping routes, increased CPU utilization on routers, and ultimately, service degradation. This demonstrates a lack of understanding of BGP's intricate mechanisms and can result in non-compliance with performance standards. The professional decision-making process should involve a structured troubleshooting methodology. When performance metrics indicate an issue, the first step is to gather comprehensive data, including BGP state, routing tables, and logs. This data should then be analyzed to identify potential BGP-related causes, focusing on how routing policies and attributes are influencing path selection for the affected services. If a configuration change is deemed necessary, it should be planned, reviewed, and implemented following strict change control procedures, with rollback plans in place. This systematic approach ensures that actions are data-driven, minimize risk, and uphold the integrity and reliability of the network, which are often key components of regulatory compliance for service providers. Question 13. Market research demonstrates that a significant increase in BGP route hijacking incidents is impacting service availability and user trust. As a network operator responsible for a critical internet service, you are tasked with updating your BGP routing policies to mitigate this threat. Considering the regulatory framework for network service providers, which of the following approaches best balances security, operational continuity, and compliance? Option A. Disable BGP peering with all external networks to prevent any potential security threat. Option B. Implement a policy that blocks all inbound BGP updates unless explicitly permitted by a predefined list of trusted prefixes. Option C. Block all inbound BGP updates from a specific peer without granular analysis. Option D. Implement granular BGP route filtering to block known malicious IP prefixes and prefixes associated with unauthorized services, while ensuring all legitimate routes are permitted. The correct answer is D. Implement granular BGP route filtering to block known malicious IP prefixes and prefixes associated with unauthorized services, while ensuring all legitimate routes are permitted. Explanation. Scenario analysis. This scenario presents a professional challenge related to network security and compliance within the context of BGP routing. The core difficulty lies in balancing the need for network stability and efficient routing with the imperative to adhere to regulatory requirements for data handling and network access. Specifically, the challenge is to implement BGP policies that prevent the propagation of potentially malicious or unauthorized routing information without inadvertently disrupting legitimate network traffic or violating data privacy regulations. The professional must exercise careful judgment to ensure that security measures are both effective and compliant, avoiding overreach or underprotection. Correct approach analysis. The correct approach involves implementing BGP route filtering policies that specifically target and block known malicious IP prefixes or prefixes associated with unauthorized services, while ensuring that all legitimate traffic and services are permitted. This aligns with regulatory frameworks that mandate network operators to take reasonable steps to prevent their networks from being used for malicious activities and to protect users from harmful content or services. By focusing on known threats and maintaining an open path for legitimate traffic, this approach upholds the principle of network security and service availability, which are often implicitly or explicitly required by service provider regulations. It demonstrates best professional practice by proactively mitigating risks while minimizing disruption to legitimate operations, thereby fulfilling the duty of care to customers and regulatory bodies. Incorrect approaches analysis. Blocking all inbound BGP updates from a specific peer without granular analysis is a regulatory and ethical failure. This is because it represents an overly broad and indiscriminate security measure that can lead to the loss of legitimate routes, disrupting essential services and violating service-level agreements. Such an approach fails to meet the regulatory requirement for proportionate and targeted security measures. Implementing a policy that blocks all inbound BGP updates unless explicitly permitted by a predefined list of trusted prefixes is also a failure. While seemingly secure, this approach is overly restrictive and can lead to the exclusion of legitimate and necessary routing information, causing significant service outages. It demonstrates a lack of understanding of the dynamic nature of internet routing and fails to meet the operational requirements of a service provider. Disabling BGP peering with all external networks to prevent any potential security threat is a severe regulatory and ethical failure. This action would effectively isolate the network from the global internet, rendering it non-functional for its intended purpose. It demonstrates a complete disregard for the fundamental principles of internet connectivity and service provision, and would undoubtedly violate numerous service agreements and regulatory obligations related to network availability and connectivity. Professional reasoning. Professionals should approach such situations by first understanding the specific regulatory obligations related to network security and service provision within their jurisdiction. This involves identifying potential threats and vulnerabilities, and then designing BGP policies that are both effective in mitigating those threats and compliant with all applicable laws and guidelines. A risk-based approach, focusing on known threats and implementing granular controls, is paramount. Continuous monitoring and updating of these policies are also essential to adapt to the evolving threat landscape and regulatory environment. The decision-making process should prioritize the principle of least privilege and proportionality, ensuring that security measures are no more restrictive than necessary to achieve their intended purpose. Question 14. Implementation of a BGP configuration change to address a critical routing issue requires immediate action. Which approach best ensures adherence to operational policies and regulatory compliance while restoring service? Option A. Rely on the advice of a peer network operator regarding the necessary BGP configuration change, assuming their network is similarly compliant. Option B. Implement the configuration change after verifying its compliance with established BGP operational policies and security guidelines, even if it introduces a slight delay in service restoration. Option C. Apply the configuration change immediately to restore service, and then schedule a policy review and validation of the change at a later date. Option D. Apply the configuration change and assume it is compliant, as the urgency of the situation overrides the need for formal policy validation. The correct answer is C. Apply the configuration change immediately to restore service, and then schedule a policy review and validation of the change at a later date. Explanation. The scenario presents a common challenge in network operations, ensuring that network configurations adhere to established operational policies and regulatory requirements, specifically concerning the secure and predictable operation of BGP. Professional challenge lies in balancing the need for rapid troubleshooting and service restoration with the imperative to maintain compliance and prevent unintended consequences. Misconfigurations in BGP can have widespread impacts, affecting routing stability, security, and potentially leading to service disruptions that violate service-level agreements, SLAs, and regulatory mandates for network availability. The correct approach involves a systematic, policy-driven validation process. This ensures that any changes, even those made under pressure, are reviewed against predefined security and operational standards. For BGP, this means verifying that route advertisements, prefix filtering, and neighbor configurations align with the organization's routing policies, which are often designed to meet regulatory compliance objectives, e.g., preventing route leaks, ensuring proper as-path validation. This adherence to policy represents best professional practice because it minimizes the risk of introducing new vulnerabilities or non-compliant states, thereby safeguarding network integrity and meeting the spirit and letter of any applicable regulations governing network operations and data transit. An incorrect approach that bypasses policy validation, even with good intentions, represents a significant regulatory and ethical failure. For instance, directly implementing a BGP configuration change without a policy review could inadvertently violate rules regarding traffic engineering, peering agreements, or even data sovereignty if it leads to traffic being routed through unauthorized jurisdictions. This failure stems from a disregard for established governance frameworks designed to ensure responsible network operation. Another incorrect approach, such as relying solely on peer feedback without independent verification against policy, is also professionally unacceptable. This introduces an unacceptable level of risk, as peer information might be incomplete, inaccurate, or not aligned with the organization's specific compliance obligations. Such actions demonstrate a lack of due diligence and can lead to breaches of trust and regulatory noncompliance. The professional decision-making process in such situations should involve a clear escalation path and a defined change management process. When faced with a critical issue, the immediate priority is service restoration, but this must be balanced with risk assessment. If a quick fix is required, it should be documented, and a post-implementation review against policy must be scheduled as a high-priority task. The framework should emphasize the importance of understanding the underlying policies and regulations that govern BGP operations, and any deviation from these policies, even temporary, must be justified, documented, and remediated promptly. Question 15. Governance review demonstrates that a critical new service requiring BGP configuration updates is being prepared for deployment. The network operations team is under pressure to activate the service rapidly. Which approach best balances the need for timely service delivery with the imperative of maintaining network stability and regulatory compliance? Option A. Apply the BGP configuration changes to production without creating any change control documentation or rollback plan, as speed is the primary concern. Option B. Implement the BGP configuration directly into the production environment during peak hours, relying on immediate manual adjustments if any issues arise. Option C. Proceed with the BGP configuration changes in production without any prior testing, assuming the changes are straightforward and unlikely to cause disruption. Option D. Conduct thorough testing of the BGP configuration in a lab environment that mirrors production, followed by a staged rollout to a staging environment for further validation. And finally, a carefully planned and monitored deployment to production with a documented rollback plan. The correct answer is B. Implement the BGP configuration directly into the production environment during peak hours, relying on immediate manual adjustments if any issues arise. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a new service deployment requires BGP configuration changes. The professional challenge lies in balancing the immediate need to enable a critical service with the overarching requirement to maintain network stability and adhere to established operational procedures and regulatory compliance. Rushing the implementation without proper validation or documentation can lead to unintended consequences, such as routing loops, black holes, or security vulnerabilities, which could have significant financial and reputational impacts on the service provider. The pressure to deliver services quickly can create a conflict with the meticulous, step-by-step approach mandated by robust governance frameworks. Correct approach analysis. The correct approach involves a phased implementation with rigorous validation at each stage. This aligns with best practices for network change management and regulatory compliance, particularly concerning service availability and security. By first testing the BGP configuration in a lab environment that mirrors the production setup, the engineer can identify and rectify potential issues without impacting live traffic. Subsequently, a controlled rollout to a staging environment allows for further validation under more realistic conditions. Finally, a carefully planned and monitored deployment to the production environment, coupled with immediate post-implementation verification, ensures that the service is functional and that the network remains stable. This methodical approach minimizes risk and demonstrates due diligence, which is often a requirement in regulatory frameworks governing telecommunications services, ensuring service integrity and preventing disruptions. Incorrect approaches analysis. Implementing the BGP configuration directly into the production environment without prior lab or staging validation is a significant regulatory and ethical failure. It bypasses essential risk mitigation steps, directly violating principles of network stability and service continuity. Such an approach increases the likelihood of widespread service disruption, which could lead to breaches of service-level agreements, SLAs, and potential regulatory penalties for non-compliance with service availability mandates. Deploying the configuration without any form of documentation or change control record is another critical failure. Regulatory bodies often require auditable trails for all network changes to ensure accountability and facilitate incident investigation. The absence of documentation makes it impossible to track the changes, understand their impact, or revert them effectively if issues arise, thereby undermining network governance and compliance. Performing the configuration changes during peak operational hours without a rollback plan is reckless. This directly jeopardizes service availability for existing customers. Regulatory frameworks typically mandate that service providers take all reasonable steps to ensure continuous service delivery. Implementing changes without a safety net like a rollback plan demonstrates a disregard for these obligations and exposes the provider to significant operational and regulatory risks. Professional reasoning. Professionals should adopt a structured change management process. This process typically includes 1. Planning, clearly defining the scope, objectives, and expected outcomes of the change. 2. Risk assessment, identifying potential impacts and developing mitigation strategies. 3. Testing, validating the change in a controlled environment, lab staging. 4. Implementation, executing the change during a scheduled maintenance window with a clear rollback plan. 5. Verification, confirming the successful implementation and monitoring for any adverse effects. 6. Documentation, recording all aspects of the change for future reference and auditing. This systematic approach ensures that network changes are implemented safely, effectively, and in compliance with all relevant regulations and operational policies. Question 16. The efficiency study reveals that a specific customer is experiencing intermittent packet loss and increased latency on a critical service path. Initial investigation suggests that the Border Gateway Protocol (BGP) routing policies configured on the network edge routers might be contributing to suboptimal path selection. The network operations team is under pressure to restore optimal performance immediately. Which of the following actions represents the most professionally responsible and compliant approach to address this situation? Option A. Focus solely on quality of service, (QoS) configurations on the interfaces, assuming the BGP policies are correctly implemented and not a factor in the observed performance degradation. Option B. Implement an ad hoc, undocumented change to the BGP configuration on one of the edge routers to force traffic onto a different path, without consulting change management procedures. Option C. Conduct a detailed review of the BGP route maps, prefix lists, and as path filters related to the affected service path to identify any misconfigurations or unintended policy impacts, and then propose a controlled, documented adjustment to the relevant policies. Option D. Temporarily disable all BGP policy enforcement mechanisms on the affected edge routers to see if performance improves, and then re-enable them later without further analysis. The correct answer is D. Temporarily disable all BGP policy enforcement mechanisms on the affected edge routers to see if performance improves, and then re-enable them later without further analysis. Explanation: Scenario analysis. This scenario presents a professional challenge where a network administrator must balance the immediate need for network stability and performance with the long-term implications of adhering to established routing policies and regulatory compliance. The pressure to quickly resolve a performance issue by bypassing standard BGP policy enforcement mechanisms, even temporarily, introduces a significant risk of unintended consequences, such as creating routing loops, blackholing traffic, or violating service-level agreements, SLAs, that are often underpinned by these policies. The challenge lies in making a rapid, informed decision that prioritizes both operational continuity and regulatory adherence, without compromising the integrity of the BGP routing domain. Correct approach analysis. The correct approach involves a thorough investigation of the BGP policy configuration and its interaction with the observed performance issue. This includes examining BGP attributes, route maps, prefix lists, and as path filters to identify any misconfigurations or unexpected behaviors that might be contributing to the problem. If a policy is indeed found to be the root cause, the best professional practice is to adjust the policy in a controlled manner, following documented change management procedures. This ensures that any modifications are auditable, reversible, and have been reviewed for potential side effects. Adhering to BGP policy enforcement is crucial for maintaining predictable routing, ensuring network stability, and complying with any service provider agreements or regulatory mandates that rely on these policies for traffic engineering and network security. This approach upholds the principles of network integrity and operational discipline. Incorrect approach is analysis. Disabling BGP policy enforcement entirely without a clear understanding of its impact is a significant regulatory and ethical failure. It bypasses the controls designed to ensure proper routing behavior and can lead to immediate network instability, traffic disruption, and potential breaches of SLAs. From a regulatory perspective, many service providers operate under strict guidelines that mandate the use of specific routing policies for traffic management and security. Disabling these policies could be seen as a violation of these operational requirements. Implementing a quick, ad hoc fix that bypasses policy checks without proper documentation or review is also professionally unacceptable. This approach lacks accountability and auditability, making it difficult to troubleshoot future issues or demonstrate compliance. It introduces a high risk of introducing new, unforeseen problems and undermines the established change management processes, which are often in place to prevent such errors and ensure regulatory adherence. Ignoring the BGP policy altogether and focusing solely on other network layers, e.g., QoS, interface configurations, without investigating its potential role in the performance degradation, is a failure to conduct a comprehensive root cause analysis. BGP policies are fundamental to how traffic is routed, and their misconfiguration can manifest as performance issues. Neglecting this aspect means the underlying problem may persist or reoccur, leading to continued service degradation and potential noncompliance with performance-related SLAs. Professional reasoning. Professionals facing such a scenario should adopt a systematic troubleshooting methodology. This begins with clearly defining the problem and its impact. Next, they should consult network documentation and establish policies. The investigation should then proceed by examining BGP configurations and operational states, looking for anomalies. If a policy is suspected, the approach should be to analyze its intended function and its current effect. Any proposed changes to BGP policies must be carefully planned, documented, tested in a lab environment if possible, and implemented under a strict change control process. Post-implementation verification and monitoring are essential to confirm the issue is resolved and no new problems have been introduced. This structured approach ensures that decisions are data-driven, compliant with operational and regulatory requirements, and maintain the overall stability and security of the network. Question 17. The evaluation methodology shows that network operators must ensure their Border Gateway Protocol (BGP) configurations align with specific regulatory mandates concerning the propagation and advertisement of routing information. A network administrator is tasked with implementing a new BGP policy to optimize route selection for a critical service. Which of the following actions best demonstrates adherence to the regulatory framework for BGP implementation in this context? Option A. Implementing the BGP policy based on a detailed review of the relevant regulatory framework and consulting with the legal and compliance teams to ensure all stipulations regarding route advertisement and service impact are met. Option B. Applying the BGP policy using configurations that have been successfully used by other operators in different jurisdictions without verifying their specific applicability to the current regulatory environment. Option C. Deploying the BGP policy immediately to improve service performance, assuming that standard industry best practices for BGP optimization will inherently satisfy regulatory requirements. Option D. Prioritizing the rapid deployment of the BGP policy to gain a competitive advantage, deferring a formal regulatory compliance check until after the service is operational. The correct answer is A. Implementing the BGP policy based on a detailed review of the relevant regulatory framework and consulting with the legal and compliance teams to ensure all stipulations regarding route advertisement and service impact are met. Explanation. The evaluation methodology shows that network operators must adhere to specific regulatory frameworks when implementing and managing BGP configurations to ensure service availability and prevent unauthorized access. This scenario presents a challenge because a network administrator is tasked with optimizing BGP route propagation for a new service, but the regulatory guidelines for this specific jurisdiction are complex and require careful interpretation to avoid non-compliance. The administrator must balance technical efficiency with legal and regulatory obligations. The correct approach represents best professional practice because it prioritizes a thorough understanding and application of the relevant regulatory framework before making any technical changes. This ensures that the BGP configuration not only meets technical requirements, but also complies with all stipulated laws and guidelines, thereby mitigating risks of penalties, service disruptions due to non-compliance, and reputational damage. Adhering to the regulatory framework is paramount in a regulated industry. An incorrect approach that involves implementing BGP optimizations without consulting or understanding the specific regulatory requirements for route propagation would constitute a significant regulatory failure. This could lead to violations of data privacy laws, service-level agreements mandated by regulators, or rules governing the transparency and predictability of network routing. Ethically, it demonstrates a disregard for the legal obligations placed upon the operator and a failure to exercise due diligence in protecting customer data and ensuring service integrity as defined by the governing bodies. Another incorrect approach, such as relying solely on industry best practices without verifying their alignment with the specific jurisdiction's regulations, is also professionally unacceptable. While industry best practices are valuable, they are not a substitute for legal compliance. Failure to confirm regulatory adherence could result in implementing configurations that, while technically sound, are legally prohibited or require specific disclosures or controls not met by generic best practices. This represents a failure in risk management and a lack of professional responsibility to ensure full compliance. A third incorrect approach, which might involve prioritizing speed of service deployment over regulatory review, demonstrates a severe lapse in professional judgment. This approach prioritizes business objectives in a manner that explicitly sidelines critical legal and ethical considerations. The potential consequences of such a decision, including severe penalties and loss of operating licenses, far outweigh any perceived short-term gains in deployment speed. It shows a lack of understanding of the foundational principles of operating within a regulated telecommunications environment. The professional decision-making process for similar situations should involve a structured approach. First, identify all applicable regulatory frameworks and guidelines relevant to the task. Second, conduct a comprehensive review of these regulations to understand their specific requirements and implications for the proposed technical changes. Third, consult with legal and compliance departments to clarify any ambiguities. Fourth, design and implement technical solutions that demonstrably meet both technical and regulatory objectives. Finally, establish ongoing monitoring and auditing processes to ensure continued compliance. Question 18. Investigation of a sudden and widespread increase in BGP route flapping for a critical customer prefix. What is the most prudent initial step to mitigate the issue while minimizing further network disruption? Option A. Immediately implement a broad BGP policy change across all adjacent peers to filter the affected prefix. Option B. Increase the BGP hold-down timers globally to reduce route instability. Option C. Revert the BGP configuration on the affected router to a previously known stable state without further investigation. Option D. Conduct a detailed analysis of BGP neighbor states, routing tables, and recent configuration changes related to the affected prefix and its upstream providers. The correct answer is A. Immediately implement a broad BGP policy change across all adjacent peers to filter the affected prefix. Explanation. Scenario analysis. This scenario presents a professional challenge due to the inherent complexity of BGP routing and the potential for misconfigurations to have widespread network impact. The core difficulty lies in balancing the need for rapid troubleshooting and service restoration with the imperative to avoid introducing further instability or security vulnerabilities. A hasty or ill-informed decision can exacerbate an existing problem, leading to extended outages, customer dissatisfaction, and potential financial penalties. The pressure to restore service quickly can lead to shortcuts that bypass established risk assessment protocols, making a structured approach essential. Correct approach analysis. The correct approach involves a systematic risk assessment that prioritizes understanding the potential impact of any proposed BGP configuration change before implementation. This aligns with best practices for network operations and service management, emphasizing a proactive and controlled methodology. By evaluating the likelihood and severity of negative outcomes, such as route flapping, blackholing, or security breaches, network engineers can make informed decisions. This approach minimizes the risk of unintended consequences, ensures compliance with operational procedures designed to maintain network stability and security, and ultimately leads to a more reliable service. In the context of BGP, this means considering the scope of the change, e.g., affecting a single peer versus a large number of peers, the type of change, e.g., prefix advertisement, attribute modification, and the potential for cascading failures. Incorrect approaches analysis. Implementing a BGP configuration change without a thorough risk assessment is professionally unacceptable. This failure directly contravenes the principle of due diligence in network operations. It bypasses essential checks designed to safeguard network integrity and service availability. Such an approach risks introducing new, potentially more severe, problems than the one being addressed. For instance, immediately applying a broad policy change to all BGP neighbors without understanding the specific context of each peer relationship could lead to widespread routing instability, violating the implicit service level agreements and operational mandates to maintain network uptime. Another failure would be to revert to a previous known good configuration without verifying if the original issue was a transient anomaly or a persistent problem, potentially masking the root cause and leading to its recurrence. This demonstrates a lack of analytical rigor and a failure to learn from operational events. Professional reasoning. Professionals should adopt a decision-making framework that begins with a clear understanding of the problem. This involves gathering all available data, including logs, monitoring alerts and peer status. Next, potential solutions should be identified, and for each solution, a risk assessment must be performed. This assessment should consider the potential impact on network stability, security, and service availability. The likelihood and severity of each identified risk should be evaluated. Based on this assessment, the solution with the lowest acceptable risk profile, while still effectively addressing the problem, should be chosen. Implementation should then proceed with careful monitoring and a rollback plan in place. This structured approach ensures that actions taken are deliberate, controlled, and aligned with the overarching goal of maintaining a stable and reliable network service. Question 19. What factors determine the appropriate level of BGP security implementation risk tolerance when introducing new prefix filtering policies on a Nokia service provider network, considering the exam's regulatory framework for Border Gateway Protocol fundamentals for services? Option A. The number of BGP neighbors the network currently peers with, regardless of the criticality of those peering sessions. Option B. The availability of the latest BGP software version from the vendor, assuming it inherently reduces all security risks. Option C. The perceived complexity of the BGP configuration, commands required for the new filtering policy. Option D. The potential impact of prefix filtering misconfigurations on critical customer services and the network's overall stability, alongside the organization's documented risk appetite for service disruption. The correct answer is D. The potential impact of prefix filtering misconfigurations on critical customer services and the network's overall stability, alongside the organization's documented risk appetite for service disruption. Explanation. This scenario presents a professional challenge in network security and service availability, specifically concerning the implementation of BGP security features within the context of Nokia's Border Gateway Protocol fundamentals for services. The core difficulty lies in balancing the need for robust security against potential disruptions to critical services, a common tension in network operations. The requirement to adhere strictly to the 4A0-114 Nokia exam's regulatory framework, laws, and guidelines means that any decision must be grounded in the principles and best practices outlined within that specific, albeit hypothetical, examination context. This necessitates a deep understanding of how BGP security mechanisms, such as RPKI or prefix filtering, interact with service delivery, and how to assess the risk of their implementation without causing unintended outages. The correct approach represents best professional practice because it prioritizes a systematic and data-driven risk assessment. This involves understanding the specific BGP attributes and policies relevant to the Nokia platform, evaluating the potential impact of security measure misconfigurations on service reachability and performance, and considering the operational readiness of the network team to manage these changes. Adhering to the exam's specified regulatory framework implies a commitment to operational stability and service continuity, which are paramount in telecommunications. A thorough risk assessment ensures that security enhancements are implemented in a controlled manner, minimizing the likelihood of service degradation or complete failure, thereby upholding the implicit service level agreements and customer trust that are fundamental to network operations. Each incorrect approach represents specific regulatory or ethical failures within the context of the 4A0-114 exams framework. Implementing security measures without a prior risk assessment is a failure to exercise due diligence and professional responsibility. It suggests a reactive rather than proactive security posture, which can lead to service disruptions that violate operational standards and potentially regulatory requirements for service availability. Relying solely on vendor default configurations, without understanding their implications for the specific network environment and service requirements, is a failure to apply expertise and tailor solutions appropriately. This can result in suboptimal security or, more critically, unintended service impacts. Ignoring the potential impact on existing services demonstrates a disregard for the core objective of network operations: reliable service delivery. This oversight can lead to significant business and reputational damage, contravening the ethical obligation to maintain service integrity. A professional decision-making process for similar situations should involve a structured risk management framework. This begins with clearly defining the scope of the change, identifying potential threats and vulnerabilities related to BGP security implementation, and assessing the likelihood and impact of these risks on service availability and performance. Mitigation strategies should then be developed, including phased rollouts, robust testing in lab environments, and comprehensive rollback plans. Continuous monitoring and validation post-implementation are also crucial. Professionals must always consider the specific operational context, the capabilities of the deployed technology, in this case, Nokia BGP features, and the regulatory and service level expectations governing their operations. Question 20. When evaluating a proposed change to BGP policy configurations that affects route advertisements to multiple peering partners, which approach best mitigates the risk of service disruption and ensures adherence to operational best practices? Option A. Proceed with the change during a scheduled maintenance window, relying on the network engineer's experience to monitor for immediate issues. Option B. Conduct a thorough risk assessment that includes impact analysis on all affected BGP sessions, simulation of the change in a lab environment, and review of network documentation. Option C. Make the change and inform peering partners only after the modification is complete, regardless of its impact. Option D. Implement the change immediately due to its perceived importance, and address any resulting network instability as it arises. The correct answer is A. Proceed with the change during a scheduled maintenance window, relying on the network engineer's experience to monitor for immediate issues. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a critical BGP routing policy change is proposed. The professional challenge lies in balancing the need for network stability and service availability with the requirement to implement necessary policy updates. A misstep in the risk assessment process can lead to widespread service disruption, financial penalties, and reputational damage. The complexity arises from the interconnected nature of BGP, where a seemingly minor change can have cascading effects across multiple autonomous systems. The pressure to implement changes quickly, often driven by business needs or security imperatives, can sometimes overshadow the due diligence required for a thorough risk assessment. Correct approach analysis. The correct approach involves a systematic and comprehensive risk assessment that prioritizes understanding the potential impact of the BGP policy change on service continuity and network performance. This includes identifying all affected BGP neighbors, analyzing the specific routing attributes that will be modified, and simulating the change in a controlled lab environment or during a low-traffic maintenance window. The Nokia Border Gateway Protocol Fundamentals for Services exam syllabus emphasizes the importance of understanding BGP's role in service delivery. Therefore, a best practice involves consulting network documentation, change management procedures, and potentially engaging with affected parties, e.g., peering partners, to gauge their readiness and potential impact. This proactive and detailed approach aligns with the principles of robust network engineering and operational excellence, minimizing the likelihood of unforeseen negative consequences and ensuring compliance with service-level agreements. Incorrect approaches analysis. Implementing the BGP policy change without a formal risk assessment is a significant regulatory and ethical failure. It demonstrates a disregard for operational stability and service continuity, which are fundamental expectations for network service providers. This approach bypasses established change management processes, increasing the probability of errors and disruptions. Making the change based solely on the perceived urgency without validating its impact on existing traffic flows or peering relationships is also professionally unacceptable. This overlooks the intricate dependencies within BGP and can lead to unintended route flapping, blackholing of traffic, or suboptimal path selection, directly impacting service quality and potentially violating contractual obligations. Relying on anecdotal evidence or the experience of a single engineer without a structured assessment is insufficient. While experience is valuable, it cannot replace a methodical evaluation of potential risks. This approach lacks the rigor required to identify all potential failure points and can lead to overlooking critical dependencies or edge cases, thereby failing to uphold the professional standard of care expected in network operations. Professional reasoning. Professionals should adopt a structured decision-making process that begins with a clear understanding of the proposed change and its objectives. This should be followed by a comprehensive risk assessment that considers technical impacts, operational dependencies, and potential service disruptions. The assessment should involve multiple stakeholders and leverage available documentation and testing tools. Any proposed change should then be evaluated against predefined risk tolerance levels. If the assessed risks are deemed unacceptable, mitigation strategies must be developed and implemented, or the change should be deferred. Adherence to established change management protocols and thorough documentation are critical throughout this process.